Bismillahirrahmanirrahim. Dear students, in this week we will learn that how to draw a shear force diagram and bending moment diagram if we start from the right end of the beam. I will consider a problem that we have already solved previously from the left hand side, and we will try to solve the same problem from the right hand side, and then we will compare our solution with our previous solution. Let's start with the problem. So we will consider a simply supported beam. Hinge support on the left side and roller support on the right side, and on half of the span, the half on the right side is acted upon by a UDL with an intensity of 5 kilonewton per meter, and we have a point load acting at this point as well. The point load magnitude is 15 kilonewton, and there is a point moment acting at this external hinge support whose magnitude is 80 kilonewton meter. This point is point A, this is point B, and this is point C. We will have one vertical reaction at this support A, and one vertical reaction at support C. These distances are 5 meter and 5 meter. We may call this reaction as RA and this reaction as RC. Now, as far as the reaction calculation is concerned, that is independent of our convention related to shear force and bending moment diagram. Whether we want to draw a shear force diagram starting from right end or left end, it has no effect on the reaction calculation. So the reaction calculation will be exactly the same as before. So let's calculate the reactions, and when we will come to the stage of drawing shear force and bending moment diagram, I will explain the difference in case when we start from the right end of the beam. Okay, so for reaction calculation, we will apply the conditions of equilibrium. Sigma Fy equal to 0 with upward forces taken as positive. So how many reactions are there acting in upward direction? Ra and Rc. So Ra plus Rc, and how many forces are acting in the downward direction? It's 15 kilonewton force minus 15 and minus this UDL, which is 5 into 5, and this sum should be equal to 0. So if I solve this, I get Ra plus Rc equal to 40, and let's call this equation as equation number 1. Now let's apply the second condition of equilibrium, and we can apply sigma mc equal to 0. Sigma mc equal to 0, and for this we can take our convention as clockwise positive. I want to keep it same as that of before. So if we are applying sigma mc equal to 0, we can start from this side. Ra is producing moment in clockwise direction about point C. So Ra into 10 is the lever arm, the perpendicular distance between Ra and point C, and Ra is producing moment in clockwise direction, so we'll take it as positive. And then we have a point moment acting at point A, and it is clockwise, so it will be plus 80. And then this 15 kilonewton force, it will produce moment in counterclockwise direction about point C, so it will be minus 15 into 5, and then this UDL, the resultant of the UDL will act at the centroid of this rectangle somewhere over here, this R, and it will be equal to 5 into 5 equal to 25 kilonewton. So minus 25, and the perpendicular distance is 5 divided by 2, and that should be equal to 0. Now if we solve this equation, we will get RA equal to 5.75 kilonewton. 5.75 kilonewton. And if I plug in this value in equation number 1, (5.75) plus RC equal to 40, and this implies RC is equal to 34.25. 34.25 kilonewton. So in this way, we have calculated both the vertical reactions RA and RC, and both have come out to be positive, which means that the assumed directions of both the reactions are correct. Both RA and RC are actually acting in the upward direction. Now, next step is to divide the beam into number of portions, and we will divide the beam into separate portions wherever we see a change in applied loading, like abrupt change in applied loading or change in the support condition. So in this case, I think portion AB and portion BC, we need to consider these two portions. I can write it down here. Portions AB and BC. Now, up to this stage, the calculations were exactly the same as that of our previous problems. From this point, when we are going to, from this point onwards, when we will be writing down the equations of shear force and bending moment diagram, starting from the right end of the beam, our sign convention will be changed. So let me write down that sign convention here. What is our sign convention when we move from left to right direction? Like our previous case, left to right. When we move in left to right direction, we take upward forces as positive and downward forces as negative. Okay, and for movement, we take clockwise movements as positive and counterclockwise movements as negative. This is our convention when we write down the equations of shear force and bending moment diagram from the left to right side. Now, what we are going to learn today is that what should be our convention when we move from right to left side, right? Or maybe it's better that I keep right and left at the same, but I change this arrow direction. Left to right to left, if we are moving in this direction. In that case, we will have to take all the downward forces as positive and upward forces as negative. And we will have to take all the counterclockwise movements as positive and clockwise movements as negative. This is the convention that we follow when we write down the equations of shear force and bending moment diagram starting from right side to the left side. And this shift of convention is required if we want to get an exactly same shear force diagram and bending moment diagram. If we do not make this change, then our shear force and bending moment diagrams will be inverted. We will not get exactly the same shear force and bending moment diagram as that of this case. So if we want to get exactly same diagram, which we want here, then we need to follow this sign convention. And you know, I'm using the word convention. So convention means something that is not absolutely fixed, or that's not a rule that is followed everywhere. Conventions are some things that we define in while solving any problem, and if we want, we can change that convention as well. But in our case, we are following this convention. If you study different books or you analyze structures using different softwares, you may find that those softwares or those books do not follow the same convention, and in that case their SFDs and BMDs are exactly opposite to the ones that we are plotting here. So that was just a general thing that I wanted to let you guys know. Now let's follow this convention and try to write down the shear force equation, bending moment equation, and finally we will draw a shear force diagram and bending moment diagram, and at the end we will have a comparison between the diagrams that we will obtain today and the diagrams that we drew previously. So as I said that we will be moving in the right to left direction. So in this case our first portion will be portion BC, because we are moving in the leftward direction now. So let's see how to do that. So the first portion that we will consider is portion BC, and the X will range from 0 to 5 meters for this portion. Okay, now let me draw the free body diagram for this portion. We have a roller support here. This is section. The intensity of this UDL is 5 kilonewton per meter. We have one reaction here, RC, whose magnitude is known to us. It is 34.25 kilonewtons, and the X in this case will start from this side. This is X, and when we are drawing the shear force diagram from the right side, now we will also consider shear and movement in opposite direction. Shear will be considered, the exposed shear will be considered in the upward direction, and the exposed movement will be considered in clockwise direction. So this completes the free body diagram. Is there anything else? I think this point we need to label this, that this point is point C. Now let's write down the equations. So first, for shear, sigma Fy equal to 0, and with the convention downward forces as positive. Okay, so if I start from this side, the first force, vertical force, is 34.25 kilonewton, and it is acting in the upward direction. So minus 34.25, and then this VDL is acting in the downward direction, so it will be taken as positive. And how much is the resultant of this UDL? It is 5 into X. So minus 5 into X, and then this shear force acting in the upward direction, so minus V, and this should be equal to 0. Now if I rearrange this equation, what do I get? V is equal to 5x minus 34.25. This is the equation of shear for portion BC, and as variable x is involved in this equation, so it means that we need to calculate the values for the two extreme points separately. So at C, x is equal to 0, so VC is equal to 5 into 0 minus 34.25, which means that this is equal to minus 34.25 kilonewton. So VC is minus 34.25 kilonewton, and at B, x is equal to 5 meters. So VB is equal to 5 into 5 minus 34.25, and this is equal to minus 9.25 kilonewton. So we have got the values of VB and VC. Now next, let's write down the equation for bending moment for the section. So sigma mx equal to 0, and this time our convention will be, we'll take clockwise movement as positive. Okay, so if we start from this side, 34.25, it is producing movement in counterclockwise direction about the section, so it will be positive. .25 into x minus the moment because of the UDL, that is 5x. 5x is the resultant of the UDL into x by 2, that's the lever arm, and then minus m because m is in clockwise direction, and that is equal to 0. Now if I rearrange this equation, I get m is equal to minus 2.5 x square plus 34.25 x. In this equation, as again x is involved, so we will calculate the value of bending moment for both the extreme points separately. M, or we can write down at C, x is equal to 0, so MC is equal to minus 2.5 into 0 square plus 34.25 into 0, and that is equal to 0. And at B, x is equal to 5 meters, MB equal to minus 2.5 into 5 square plus 34.25 into 5, and if we solve this, what do we get? We get positive 108.75 kilonewton meter. So the value of bending moment at support C, which is an external roller support and not subjected to any externally applied moment, comes out to be 0, this value here. So this is totally fine. External roller. So this is an external roller support, and the value of bending moment at this location is equal to 0. So this completes our calculations for portion BC. Now let's move to the next portion, portion AB. Okay, for portion AB, x will range from 5 to 10 meters for this portion. Let's draw its free body diagram. The entire UDL will be present in this part. Roller support is present here, section is over here. This point load will also appear in this free body diagram, 15 kilonewton. Intensity of this UDL is 5 kilonewton per meter. This point is point C, this point is B, and the exposed forces are V in upward direction and M in clockwise direction. This RC is also known. Okay, RC is how much? RC is 34.25 kilonewton, and this distance is x. Okay, 34.25 is the reaction, and its distance from the section under consideration is x. Now let's write down the equation of shear force and bending moment. For shear force, we'll take sigma Fy equal to 0, and our convention will be that we will take downward forces as positive. So starting from point C, we have an upward force of 34.25, so it will be taken as negative, minus the entire UDL, sorry, not minus but plus, because it's acting in the downward direction, 5 into 5, and then plus the point load 15, and minus shear V, and this should be equal to 0. If I rearrange this equation and solve it, I get V is equal to 5.75 kilonewton. So this is the value of shear for portion AB, and it's a constant value, which means that we do not need to calculate this value separately for point A and point B. Now let's apply the equation of moment. Sigma mx equal to 0, and our convention will be we'll take counterclockwise movement as positive. So starting from this end C, how much is the lever arm of this 34.25 kilonewton with respect to the section? It is x, and it is acting in or it is generating movement in counterclockwise direction. So it will be taken as positive 34.25x. Then this UDL, the resultant of the UDL will act at the center of the rectangle, somewhere over here. This is the resultant. 5 into 5 equal to 25 kilonewton. And how much is the distance between this resultant and the section? Now the portion present on the right side of the resultant, this part is 2.5 meters. So the distance between this resultant and the section is x minus 2.5. So minus 5 into 5 is the magnitude of the resultant, and x minus 2.5 is the perpendicular distance between the resultant and the section. And then this point load, it is also producing movement in clockwise direction about the section. So with a negative sign, 15 into x minus 5 minus m is the exposed movement, and this is equal to 0. Now if we solve this expression, we get 34.25x minus 25x plus 62.5 minus 15x plus 75 minus m, and that is equal to 0. Now if we solve it further, we get m is equal to minus 5.75x plus 37.5, and this is the equation of bending moment. And as this equation has x in it, it means we need to calculate the value of bending moment separately for point A and point B. So let's calculate those values. At A, x is equal to 5, or we are let's calculate it for B first. So at B, x is equal to 5 meters. So MB, if we plug in these values here, minus 5.75 into 5 plus 137.5, it comes out to be 108.75 kilonewton meter, and this is exactly the same value of MB that we got from portion BC. And then at A, x is equal to 10 meters. So MA will be equal to minus 5.75 into 10 plus 137.5, and it turns out to be 80 kilonewton meter. And this 80 kilonewton meter, if you look at our given problem, this A is an external hinge support, but it is subjected to an externally applied moment of 80 kilonewton meter. So this value of 80 should appear, we expect that it should appear at the external hinge support in bending moment diagram, and we are getting the same value here as MA. That totally makes sense. So this completes our calculation for shear force and bending moment diagrams. Now let's draw these diagrams, and then we will have a comparison of these diagrams with our previously drawn diagram. Okay, so let me draw the beam here once again. So we have a simply supported beam subjected to a UDL point load and a point moment, 80 kilonewton meter. This is 15 kilonewton. The intensity is 5 kilonewton per meter. This point is A, this point is B, and this point is C. The reaction here is 5.75 kilonewton. The reaction here is 34.25 kilonewton. Okay, and these distances are 5 meter and 5 meter. Now, in order to draw shear force diagram and bending moment diagrams, we need some guidelines. So let's draw the guidelines. Here are our guidelines. Okay, so for SFD, this is our 0, 0 line. We are drawing SFD and the units are kilonewton. Now, how much is the value of shear at, yes, we will draw this diagram from the right side. So how much is the value of shear at point C? We calculated that, and that value is minus 34.25. So let's say it's somewhere over here, minus 34.25. And how much is the value of shear at point B? It's 9.25 with a negative sign, so let it be somewhere over here. And the if we look at the degree of here, if you look at the degree of this equation, the equation of shear for portion BC, it is first degree equation. That's why I have joined these 2 points with a straight line. So this is 9.25, 9.25. And then what is the value of shear for portion AB? The value of shear is for portion AB is constant. Here we calculated on the same page, 5.75 kilonewton. So for portion AB, the value of shear is constant, positive 5.75 kilonewton. 5.75. Here it is, 5.75 kilonewton. So this part of shear force diagram is positive, and this part of shear force diagram is negative. This completes the shear force diagram for the simply supported beam. Now let's draw the bending moment diagram. 0, 0 line, and this is BMD. Units are kilonewton meter. How much is the bending moment value at support C from portion BC? If you check your calculations, it's equal to 0. And how much is the value of bending moment at point B? It is 108.75 kilonewton. So it's somewhere over here, 108.75 kilonewton. And this is the equation of bending moment for this part is second degree. So it will be, these 2 points will be joined with a second degree line, and the slope of second degree line depends upon the magnitude of shear force diagram. The magnitude of shear force diagram, as we move in the rightward direction, the magnitude is decreasing, so the slope of bending moment diagram should also be decreasing. So the curve will be somewhat like this. If we proceed in the rightward direction, the slope of bending moment diagram is decreasing. And then in this part, the value of MB from portion AB is exactly the same, 108.75, and the value of MA, we have just calculated here, it's 80 kilonewton meter with a positive sign, so it will be somewhere over here. And the equation of bending moment for portion AB is first degree, so these points will be joined together with a first degree line. This line is second degree, whereas this line is first degree, and this value is 80. And this completes the bending moment diagram for this part. Positive. So this completes the shear force diagram and bending moment diagrams for this beam. The last part is to draw the elastic curve. As the entire bending moment diagram is positive, so we will be drawing the entire elastic curve as sagging. Here is that. The entire elastic curve of the beam is sagging. So this is the shear force diagram and bending moment diagram for the simply supported beam drawn from the right side of the beam. Now, as I said earlier, that this is one of the problems that we have already solved starting from the left end of the beam, and today we discuss the sign convention when we start from the right side. And as I mentioned earlier, that finally we will compare our solution, our today's solution, with our previous solution, that whether we have got exactly same shear force diagram and bending moment diagram or not. So let me show you the previous solution. Now here is our previously drawn shear force diagram and bending moment diagram. You see, this is our previous solution. It's exactly the same beam, and here is our shear force diagram and bending moment diagram, and this is our new solution. Let me try to bring both of them in the same frame. I think it's a bit hard, but you can surely get an idea. This is old solution, right? And this is our new solution. That in new solution we are getting exactly the same shear force diagram and bending moment diagram with exactly the same values. So this verifies our calculations, and as we claimed at the beginning that we will be changing our convention in order to get exactly same diagrams. Now if we had not changed our convention, then we would have got exactly a mirror image of these diagrams. Whatever is positive shown as positive here, we would have got that as negative. So that's the difference that would have been there. In general, I always suggest my students to stick to one convention, and most of the time we start from the left end and we always stick to that. But in some of the cases it is simpler to start the problem from the right end. When we have, for example, if you have a complicated beam having a combination of different loadings, and you want the value of bending moment at any particular point, let's say at this point, and you have like 5 different types of loads on the other side. So starting the solution from the left hand side will be much more complicated as compared to starting the solution from the right side and quickly getting the desired value. Okay, so every time in future when you will be solving problems, you will be doing structure analysis and design of structures. Every time we do not need the entire shear force diagram and bending moment diagram. Sometimes we just need value of shear or bending moment at a particular location. In that case, if the location is close to the right end and a lot of complicated types of loads are present on the left side of that section, then it is much simpler to proceed the problem from the right side. So in that case, this today's lectures convention will help you. So with this, I think we have completed this problem. So I will just stop recording here. Thank you very much.